Hey class, I just wanted to finish off the problem we never quite got to finish in class today. This one about the medical tests and trying to figure out what is the probability of having the disease given that you tested positive. So D plus is having the disease, D minus is not having the disease. D plus is testing positive, T minus is testing negative. So this is what we're after, is this, oops, should better do that conditionally. The probability of having the disease given that you've tested positive. Now, if you have a table, this is pretty straightforward, but it does take some work at times to make the table. But once you get that, then you can think of the column of testing positive. So this is the positive testing column, and you can simply do the ratio of the positive, like those that actually have the disease of those that test positive, divided by the total. So we could, if I did this right, I should have 297. So 99 over 200, about 200,000. So that is the probability of actually having the disease. It's quite small. We'll come back to that, or we'll talk about it next time in class, the actual size of that. So, because this is the total number of people right here, this is the total number of people that tested positive, right? It's the sum of that positive row, and the number of people that have the disease is 99. Okay, that's one way to do this problem. So you can build a table. Tables are nice, but they do take a little work because most problems don't give you all of the numbers you need to fill in. You have to do some calculations and reasoning. If you have, I also went and I finished the tree diagram. So the probability of having the disease is 1 out of 100,000. So 999,999. That's probably not 0.99999, etc. And then if you have the disease, the probability that the test will come back yes is 99. It's 1%. If you don't have the disease, you have a 2% chance of it saying that you do, and a 98% chance of it saying that you don't. And I multiplied those, multiplied the paths to get each of those, and these are the numbers you end up with, and you'll actually see a connection between this set of numbers in green here and the numbers in the table. I just multiplied those by 10 million, and you get the numbers in the table. But these are probabilities already. All of these will add up to 1. I'll come back to the tree diagram. So Bayes' theorem, which we derived, says if I want a conditional probability, I can get that by, like, the probability of A given B. If I take the probability of A times the probability of B given A and divided by the probability of B. So we can use this formula. We had 2 of the 3 pieces already. We just needed to talk about this bottom piece right here. Oops, it didn't work. Just need to talk about this bottom piece, because the probability of testing positive, or the probability of having the disease, is 0.00001. And that's just taking it off the table there. The probability that you test positive given the disease, so given you have the disease, we're in these areas, probability that you'll test positive is 0.99. 0.99. Now the probability of testing positive, this one we don't have directly off of the tree, we have to do one quick calculation. We can get it here. The probability of testing positive is this number divided by the total. So it's 0.200057. Oh, 0.02. But I wanted to get it off this tree diagram so you knew how to do that. So the probability of testing positive, well, the two places you could test positive are here. You can have the disease and test positive, or you cannot have the disease and test positive. Okay, so those are the only two places. So these are already probabilities. So since this is an or situation, I can test positive by having the disease or by not having the disease. I can add those up, and if you add those up, you get the 0.8 plus the 9 will give you a 17, carry the 1, etc. You do all that, you'll get this 0.0, then that number. So 0.0200097. And if you'll notice, if we multiply the numerator and the denominator by, that we can calculate now, right? Punch that into a calculator. That will tell us what that is. And notice that is the same thing that we had up here. So it's equivalent. We just have to multiply everything by 10 million. So 1, 2, 3, 4, 5, 6, 7. Move that over 7 decimal places. If I move this over 1, 2, 3, 4, 5, and this over 2, gets us our 7 decimal places. I just get 1 times 99. So the tricky part was getting this from the table and recognizing, oh, the probability of testing positive is like where I end up off on these two tracks. I can have the disease and test positive. I cannot have the disease and test positive. So I take those two probabilities and add those together. Sometimes you'll see Bayes' theorem with a sum in the denominator. I don't know exactly how they would write it, but they might write it as conditional probabilities. So I suppose they could write it this way: the probability of t plus times the probability of t plus given d plus all over, and then here it would be the probability of testing positive given you tested positive, plus the probability of testing positive given am I doing this right? Yeah, given that you do not have the disease. Probability of testing positive given that you have the disease, and the probability of testing positive given that you don't have the disease. I think that's how they would write that. This way has some advantages because it generalizes. So suppose you don't just have two options with have the disease and don't have the disease. Suppose you had 3 options, some context where you had 3 options. Then you could generalize that to I'm just going to keep the d plus for now. Oops, that's times t plus given d plus over, and that probability of t plus given a plus the probability of testing positive given that you're in the B situation, and the probability of testing positive given you're in the C situation. So these, like in your homework, you'll be able to use to generalize it to these, because you're going to have 3 pictures. So this is what you have to do